Hello, my name is Leonardo and I'm going to present the results of our research, the DeepONet for Finance, an approach to calibrate the Heston model. This is our agenda, an introduction, data and methods, computational experiments, and then the results, and finally the conclusion. The introduction. The stochastic models, they are an attractive way to describe the evolution of dynamical systems. They are a natural choice for modeling complex systems under uncertainty. There are several applications for stochastic model. Among them, protein kinetics, hydrology, finance, that is the focus of our study, structural mechanics, and others. However, the parameter calibration of a stochastic model is a challenging task. So the Heston model was introduced by Heston. Was the first model, the first stochastic volatility model, and is the most popular one. This model was the first to capture the non-constant volatility features in the financial market. The problem of calibrating the model parameters has been a challenge in the next 2 decades. And this study focused on the Heston model calibration using neural networks and historical time series. This is the Heston model. The Heston model assumes a dynamic of the price x at the step t, which follows a geometric Brownian motion, GBM. The instantaneous volatility upsilon at the step t is governed by a mean-reverting square root stochastic process, or a SIR model. This is the Heston model. We're interested in the 5 parameters here shown in blue, and the figure in the left shows a comparison of 2 stochastic models produced by the GBM in red and the Heston model in blue, while the figure in the right shows the volatility. We can see that the volatility for the GBM is constant, while we have here time-dependent volatility for the Heston model. So, data and methods. Let's talk about the DeepONets, the focus of this paper, of this study. Liu et al. Proposed DeepONets to learn dynamical system operators using neural networks. The parameters are learned by the neural networks. The DeepONet was developed around 2 subnetworks. The branchnet here. The branchnet encodes the input function using a standard neural network, and the truncated shown here. This network is a second branch decoding the location for output functions. I here can be a function of the inputs or exogenous time series or exogenous data, exogenous information. The results of the outputs of these 2 neural networks, they are combined to provide output for the DeepONet. The DeepONet is divided in 2 types, in 2 classes, a stacked DeepONet and unstacked DeepONet. In the stacked DeepONet, a neural network is constructed for each input, while in the unstacked DeepONet, a single neural network uses as input all the information of this vector u. This is the main difference between stacked and unstacked DeepONets. Let's talk about the calibration methods. The literature about calibration processes is concentrated on cases where the volatilities are unknown and the researcher has no information access to the market price or implied volatilities. We are considering here the case where we have unknown volatilities and they are based only on the historical data, historical time series. There are some studies in the literature, for example, a GARCH approach to the model calibration, and also a comparison here for different architectures for multilayer perceptrons to calibrate a geometric Brownian motion. Just remember, again, we are trying to calibrate these 5 parameters of the Heston model shown here in blue. In this paper, we have 4 models to calibrate the 5 parameters of the Heston model using historical data. The 4 methods are stacked and unstacked DeepONet, a GARCH approach, and a multilayer perceptron. The dataset was generated using 5,000 trajectories, 5,000 time series, with 2,200 steps each one. We have simulated the time series based on the Heston models with known where the parameters they are known. The data was split in 80-20% to training test, and we have used in this study the mean square error as the performance metric. So this is the flowchart of our study. In the first step, the simulation step, the data set is generated. We collect a set of 5 parameters and store them in a parameter set, and then we run a Monte Carlo simulation and store the time series in this time series data set. Then these 2 data sets, they are concatenated in a unique data set that is split in the training dataset and the test dataset. The training dataset is used in this training step. The time series, they are used to feed the branch net, and we use a feature structured specific for time series and principal component analysis to feed the trunk net. These neural networks, they are used to construct an output for each parameter. So we have here 5 neural networks. These neural networks, they are trained, and then we go to the test step. In the test step, a similar procedure in the training step is performed here, and the processed data is used to predict the parameters, the 5 parameters of the Heston model in the test data. We also use the test data to estimate the parameters using GARCH and the fully neural networks, and then we compare the results. Given this flowchart, we go now to the computation experiments and then the results. This is the evolution of the training for the 5 parameters. Here we compare the stacked, unstacked, and unstacked DeepONet, the stacked showing green, the unstacked showing in blue. So we can observe that for a parameter eta, shown here in D, we can observe an overfitting by the difference between the train and the test loss. And here we have the overall results. We have arranged the mean square errors in box plots, and we can see that for the parameter alpha, GARCH produced the better results for alpha, and for parameter eta we can see the best results comparing the median, the interquartile, and also the outliers for these two box plots. For parameter rho, the fully neural network has produced the smallest mean square error averaged for all test set. And for parameters sigma and upsilon, the unstacked DeepONet produced the smallest mean square errors. Here a plot of the results for the 5 parameters. You can see that the GARCH produced the smallest average mean square error for 2 parameters. DeepONet also for 2 parameters, and the fully neural network for parameters rho. And now the conclusion. The results of this study show that the neural network approach is a data-driven alternative to calibrate the Heston model, and the unstacked model is equivalent with the fully neural network in 3 out of 5 parameters. We can see that also that an increasing complex topology for the DeepONet could not reflect in the precision gain. Considering the results found in this study, the ongoing research includes some pre-processing steps to extract more time features of from the time series, and also the comparison with another tools such as Gaussian processes, Markov chain, reinforcement learning, and long short-term memory neural network. As you can see, as we observed in this paper, in this study, the GARCH produced the smallest mean square error for 2 parameters, DeepONet for 2 parameters, and the neural network for 1 parameters. And further research is to consider ensemble models to investigate their prediction errors and also the associated computational cost. So I would like our university and also the Brazilian agencies for funding our research. And thanks for watching.